Hello grade 11s, great to be back with you again. Today we're starting an important section. We're going to be revising what light is all about. So we've called it investigation of light. So let's see if you would come with me what we're going to be covering today. We're going to be investigating light, and in this particular section we're going to be looking at a number of key ideas. So in today's session we're going to start by explaining what light is, or try to, where does light come from, and why is it important for us to know? Well, this is an age-old question, something that you need to think about. Let's move on. We're also going to identify what happens when light strikes the surface of different objects. And out of that process, we're going to explain the processes of reflection, refraction, total internal reflection, and something called diffraction. So guys, it's a really cram-packed session. What we're going to be focusing on today is the phenomena. We're going to be drawing diagrams and explaining. We're not going to be doing any calculations. The calculation work that's related to light we will put into the next session. So let's get busy and let's try and answer some of those questions right from the start. Here we go. So what is light? And you might have wondered, just like probably people throughout the ages have wondered, what is light? They might have been sitting on the beach and watching the sunrise and noticing it, or looking up at the moon and seeing light coming from the moon. On a starry night, watching the twinkling of the stars on a clear night. Where does this light come from? What is light, and what do we need to know about it? Now, the interesting thing is that scientists throughout the years have put forward different propositions, different ideas about light. In fact, some of the major physicists have all made contributions as far as light is concerned. If we think about great men like Newton and Einstein, and others like Maxwell, they have all contributed something to our understanding, our modern understanding of what light is. So let's begin right from the beginning and recognize that first of all, that light is part of the electromagnetic spectrum. So it's an electromagnetic radiation, and we can therefore say it's part of a set of waves, electromagnetic waves. Now, because it's a wave and it's an electromagnetic wave, we need to recognize something and remind you that all electromagnetic waves have something very special about them. They have a constant speed, and that speed is given as the variable or the constant c, written as a symbol c, and we say it's 3 times 10 to the 8 meters per second. Now, in terms of speed of objects and light and all that, one of the most famous discoveries attributed to Einstein is his theory of special relativity and general relativity, and he actually went on to state that nothing can go faster than the speed of light. So it's a really important idea. Now, when we're talking about light and we're talking about electromagnetic radiation, we've got a particular idea. It's part of that band of special waves, special radiation that comes from around us, including radio waves, television waves, X-rays. They have different amounts of energy. The visible spectrum, as you no doubt remember, has a certain amount of energy. So in its purest form, we can think of light as energy. And what it's doing, it's using this electromagnetic radiation or electromagnetic wave to transport packets of energy. Energy from the sun comes to us because of electromagnetic radiation. Energy comes through space because electromagnetic waves don't need a medium to pass through. So we're getting the benefit of this energy from the sun, all the way from infrared all the way to ultraviolet coming from the sun and some others, but we're observing light. We have receptors in our bodies, namely the eyes, that can take in light. And so what we need to recognize in its purest form, light is energy. But we've moved on. Where does it come from? It comes from sources of light, and the main source for us is the sun. And we recognize that these sources of light are called luminous objects. They're luminous objects. They give off energy because of either being heated or because of their chemical reactions that are taking place in them. They are giving off this energy which we observe as light. So I hope you've got that very clearly. So when we turn on a light switch and we light up an incandescent bulb or we light up a compact fluorescent, what we're doing is we're exciting and giving energy to either the electrons in the wire of the filament, and they move around and bump around, and that little filament gets really hot, and it gets so hot that it eventually glows and gives off light. Or in a compact fluorescent, we're giving electrons in the gases energy, and they're releasing some, or the atoms in that gas, and they're releasing some of that energy as light because they can't stay excited forever. So what we need to recognize is around us we have sources of light. I'm standing in the studio surrounded by lights that are falling on me. But there are other objects that do not emit light, but they reflect light. We see them because light falls on them from a luminous object. We say these objects are illuminated. So we sometimes get light from illuminated objects. They are not sources. They are not sources of light. They simply reflect light. So we see the world around us because light from luminous objects falls on the objects, and we can then see the reflected images through our eyes. So why is light important? Well, first of all, and I think that you wouldn't be wrong in saying this, it gives us a much easier and better sense of the world. We can see because of light. We see because of light. And so navigation and being familiar with the world around us is possible because we're able to receive this light and sense it and make sense of our world. So for us as human beings, that's really important. Light, without light, and there are many unfortunate people who are blind, but they've learned to cope with that blindness. But if everyone was blind, what a terrible place it would be. We wouldn't have the full experience of our beautiful world. So we really sympathize and empathize with people that are blind or have vision defects. We need to recognize how fortunate we are and appreciate our eyes and recognize that without them, our life would be really quite dull. And we would not be able to make sense of the world around us as much as we are. If you think about all the information we gather through our eyes, either by reading a book or watching a television program or engaging on a computer, all of that depends on a visual form of us being able to receive information. So I hope you can see that's important. But there's another aspect that I want to stress for you, and that is because light is energy, you will be sure to remember that we need food. And energy from the sun is converted in a process of photosynthesis. Photo, meaning light, synthesis, meaning to build. So plants and organisms that have chlorophyll in them would be able to photosynthesize. They're able to take the energy from the sun and convert it in an amazing process to make food for us. Without this, we would not survive for two reasons. One of the processes or products of photosynthesis, as I've mentioned, is food, which is really important, but the other is oxygen, byproduct of oxygen. Without these two things, life would not exist. So I hope you can see that light is very important. From a physics point of view, our understanding of light and what makes it possible for us to see and all those sort of things, the theory of light, is it a wave, is it a particle, has helped us to understand the very nature of matter. So the discoveries relating to light have helped us to broaden our understanding of many other fields of physics. So that's why, three reasons why we would say that light is very important and a very important aspect of physics. So let's move on and let's go and find out more about light. So the first thing we want to say is, what happens when light falls on an object? Well, it depends what type of objects. We know that there are different types of objects around us. And so I'm going to start with the most basic one first. I'm going to say, let's take something like even my skin. We recognize that when light falls on my hand, and you can see it coming from the studio, lights over there, light falling on my hand, what's happening to it? Well, there are two things that are happening that are very important for you to understand. This object, my hand, light is not passing through it. Light is just interacting on the surface. Two processes. When this happens, light cannot travel through the object. We say the object is opaque. Opaque. And that means that light does not travel through. So what happens to the light? The first thing that you need to recognize is that you can see my hand. The light from the luminous object has illuminated my hand. My hand is an illuminated object, and my hand has reflected back into the camera some aspects of light, some frequencies of light, some colors of light. And so you can see the image of my hand. So the first thing I'm going to write down is an opaque object can reflect light. When we talk about reflection, we simply mean light is falling on it and it's bouncing off it. Okay? But there is another important thing that we need to understand that's happening at many surfaces. And that is, on the surface, the atoms of the material are able to interact with the light energy, and they're able to absorb it. Much like chlorophyll is a chemical that absorbs green light, or uses the light, and we see it as green, uses frequencies, doesn't absorb the green light, we see it as green. It absorbs all the frequencies other than the green frequency, and it absorbs those, and it reflects green light. So that's an important idea. So objects absorb light, and we see them as different colors because of the frequencies they have absorbed. We see the reflected frequencies. Okay, so let's just make this very clear. We recognize opaque objects do two things. They reflect light and they absorb light. Without going into too much detail, we recognize that different colors will reflect different amounts of light. A white object will reflect all the colors of light that are shone onto it, because we know that light from the sun is a mixture of colors from red through to violet. Now, if we see an object that is red, what's happening? What's happening? The red object is absorbing all the frequencies except the red frequency. It's reflecting the red. What about a black object like my shirt here? It's absorbing all the frequencies and it's reflecting nothing. In fact, what you're seeing, the reason you see black is because all the light has been absorbed. So you see nothing in its place. When we see nothing, we see something dark, we see black. And that's how we know when something is being illuminated and when it's not illuminated. If there's black around us, black means the absence of light. Hope you've got that. Now, that was the first type of substance or object. Objects that are opaque, reflect light, and they absorb light. Secondly, we can get translucent objects. Change the color, just so that we've got it. We'll call this translucent. Now, a translucent object, yes, that object can also reflect, it can also absorb, but it allows light to pass through it to a certain extent. So it will reflect because we can see it, it will absorb, but more importantly, it allows transmission. It allows light to travel through it. It allows light to travel through. But not all light. So I'm going to say partial. So when we say a translucent object, we're thinking of something that's colored. So for example, if you take different plastic bottles, waste plastic, and you look at them, some of them will be clear, some of them will have a color to them. They don't allow all the light to travel through them. We can see dimly through them. We could even take as an example of a solution. If you put some mud or some clay into water, you can still see it a little bit. It's a bit murky. Light is kind of passing through, but you can't see clearly as if it's crystal clear. So please notice the difference between those. When something is translucent, it's not opaque, it allows some light to travel through it. But then what happens if something is clear? What do we call that? It is something that is transparent. Then it will allow all the light falling on it, light, to pass through. It doesn't prevent it from going through it at all. On the surface, we might get some reflection. Well, we will get some reflection if we can see it's in a container. We can see that reflection, that object, so we can identify, yes, that's a glass block. If we look into a glass full of water, we can see the water level. There is some reflection, but if we shine a bright beam of light on, we'll recognize the beam of light will travel straight through. It's not impaired, it's not hindered from passing through the particular substance at all. So please bear this in mind. We need to recognize that there are different types of substances and three possibilities can occur. It can be absorbed, can be reflected, or it can pass through. So what I want to do next then is to investigate each of these processes. I'm not going to say too much more about the absorbing process. You don't need to know much more about that, and there are no calculations related to that. What I want to look at next is to query and to investigate what happens when light falls on a surface and it is reflected. What's the process of reflection all about? Let's have a look. So, reflection of light. What I've got here is a grey block, which I wanted to represent a mirror. So, what we're seeing here is a grey mirror, and I'm wanting to draw in, at the surface of this mirror, a beam of light striking at that point. So I want to get them right in the corner so that it's adjusted correctly. There we go. Now, when we deal with reflection of light, what we need to recognize is that light falling on a mirror coming in is called the incident ray. And we're drawing it as a straight line there to indicate that light does travel in our thinking of light is like beams. It travels in straight lines. It radiates out from a source. And so we recognize that this is an accurate representation, and it's a very useful representation of, for experimental purposes. We recognize light is moving towards the mirror, and it strikes the mirror at a point. Now, what's this dotted line? The dotted line that I drew in before on the slide is called the normal. And a normal is an imaginary line that is at 90 degrees, perpendicular, in other words, to the surface, at right angles to the surface. Okay, got it. So, what happens? We need to recognize that the angle that is formed between the normal and the incident ray is known as the angle of incidence. So this angle measured from the normal is known as the angle of incidence. This one, angle of incidence. Right. Now, very important for you to understand is that when the light strikes the mirror, when we draw it, we recognize that there is something coming off it. That we will call the reflected ray. I'm going to put that in so we can make very sure that we've got it right. So over here, I've got the reflected ray. And that's telling us that the beam of light has been reflected from the surface of the mirror. When you do this, and you do these drawings for tasks, you would need to use a protractor and you'd need to use a ruler. So be very clear about that. This beam of light is known as the reflected, it's the reflected ray. And the angle inside here between the normal and the reflected ray is known as the angle of reflection. So what can we say about the relationship between the angle of incidence, the normal, and the angle of reflection? Now there are two things, and these are noted in what we call the laws of reflection. Let's have a look at them. Here they are. As I said, there are two parts to these laws. The first one says the incident ray, the reflected ray, and the normal are all in the same plane. What do we mean by that? It means you can take a piece of paper, and if you've got the normal, the incident ray over here, the normal will lie on that same piece of paper, and so will the reflected ray. They're all in one plane, whether that plane is vertical, horizontal, or at an angle. So if there's a surface like this, where there's an incident ray coming down onto the surface, then the normal will be at 90 degrees to the surface, and the reflected ray will be in the same plane. It's not going to bend like a spinning ball from a cricket spinner. It will go in the straight line. Where it was put in, that's where it will come out. In a straight line. You'll be able to look behind them and they will all line up. The normal, the incident ray, and the reflected ray will all be in one straight line. In a piece of paper, on a piece of paper, in the same plane. Now, the next part is the one that we use most often for drawings and calculations, and that tells us the angle of incidence is equal to the angle of reflection. We would say that theta I is equal to theta r. in this context. The angle of incidence is equal to the angle of reflection. So guys, please make sure that you've got that sorted out and you're very clear about what's happening. Now, this is what is going to happen in most cases. It will certainly happen for opaque objects. It will happen on the surface, a shiny surface of a translucent object, and even on a transparent object, piece of glass. You can sometimes see reflection taking place from there. It's all because of this particular property of light, that light is able to bounce off surfaces. It's able to be reflected. And it's a good thing. Without this reflected light coming to us, we wouldn't hardly know the world. If it wasn't for reflection, all we would see is those luminous objects around us, and that would be quite terrible. So let's move on, and I just want to introduce the next idea, and we're going to go on to that. After the break, we're going to look at something called refraction. This is what happens when light passes through an object. What happens when light passes through a transparent object or even a translucent object. We're going to need to understand this process of refraction very well, because it's a fascinating topic and there are lots of calculations that we can do with this. So don't go away. Take a stretch, take a break, make sure that you've understood everything that's happened in this first part of the lesson, and when we come back, we'll dive into refraction. Welcome back, guys. Let's dive into the idea about refraction now. So what is refraction? Well, what I mentioned to you earlier is that when light passes through a transparent or translucent object, it will travel through it. But there's an important change that takes place. Remember that in a vacuum, and also very much close to air, we know that the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So what happens when light enters other media, other examples of materials? Then there is a change in speed. So if the material is what we call optically dense, it's going to cause those electromagnetic waves to slow down quite significantly. If it's not optically dense, but the particles allow light to travel through it, then we would say that the speed of light in that material could be quite close to the speed of light in a vacuum. So there is a relationship that we need to understand when we deal with refraction that is dependent on the change of speed. And if you understand that refraction is all about how the speed of light changes, then you won't have a problem. So scientists around the world and through time have been trying to measure the speed of light and have in fact measured the speed of light in different objects. And the easiest way to look at this change in speed is to come up with a constant for each material. And we call that constant the refractive index. So the refractive index, N, okay, just underline that, of a material is the ratio of the speed of light in a vacuum to the speed V of the light in the material. So there's the simple equation. We've got N is equal to the speed of light C divided by the speed of light in the material, which we give a symbol of V. So let's look at some common refractive indices. And what you'll recognize is, as I mentioned, that something like air has a refractive index of 1. So what does that mean? It means the speed of light in air and the speed of light in the vacuum are the same. It's this number divided by that number gives a ratio of 1. So that means that in air, the speed of light is very close. We've rounded it off, but it's very close to being the same as the speed of light in a vacuum. So be aware of that. What you need to recognize is for these other refractive indices, what's happening. You'll notice that all the other values that are given here are getting bigger. That tells us that the speed of light in the material is slowing down. It's less than c for these materials down here. So if we look at something like plastic, refractive index of 1.46, something like diamond, very high refractive index of 2,42. What does that mean? It means to get an answer of 2,42, the speed of light in the material must be much smaller. It's in fact 2 times smaller, more than 2 times smaller than the speed of light. Notice that that speed will still be in the region of a fraction times 10 to the 8. Okay? It won't be times 10 to the 4 or something like that. That doesn't happen. What we need to recognize when we're doing the calculations, we'll come back to this particular point. You need to check your calculations and make sure that you get a reasonable answer. Okay? So be aware that if the refractive index is high, then that tells you that the speed is slow. So there's a relationship. When n increases, then what we're going to say is that tells us that the v, the speed of light, decreases. In this respect, they are inversely proportional, because we can rearrange the formula to say n is equal to c over v, and what you can recognize then is to see that v is equal to c divided by n, and all that you're doing, that's a constant, and what does that tell you? It tells you we can write it as v is inversely proportional or directly proportional to 1 over n. Inversely proportional. Very important that you understand that idea. Excellent. We will move on from that and we'll look at some examples now to show what happens when light enters different objects. And we are taking for granted that these are transparent objects where refraction will take place. So what's the first example we want to look at? We want to look at the refraction of light through a rectangular, you need to know this, a rectangular block. It could, in our case, it's a glass block. Notice something here, that the refractive index of light in the refractive index of air is given as 1,0, with the refractive index of glass, which is in there, is going to be 1,52. So what do we recognize? Over here, it's going to be going fast, and here it will slow down. So light entering the glass is going to slow down. When it leaves the glass on the other side, it's going to speed up. It's going to be fast. So the light traveling through the block is going to be fast, slow, fast. It's going to, in other words, go slow down and then speed up. Make sure that you understand the terminology and that you've got it very clear. Now, how can we determine what's going to happen? Well, there is a law that we'll take a look at, but I want to do the explanation first so that you've got it very clear what exactly is happening. Now, you will not notice the change in light when it acts at a particular angle. So it's dependent on the angle and the material. So if I have light, incident ray here, the incident ray forms an angle of incidence equal to 0 degrees. Remember, we always measure the angle between the normal. So it's lying on the normal. Then what's going to happen? Well, what we observe when this happens is that light travels in a straight line and it passes straight through. I just want to get that so it's all lined up like that. So we don't see any change in direction. All we know is that there's a change in speed. And that's very important for you to recognize. What's happened? It was going fast here. It slowed down. It was slowing down, and it was increasing in speed. It went fast again. We might not have seen or observed anything because the angle of incidence was equal to 0. In other words, the angle between the normal and the incident ray was 0. Got it? You must make sure that you understand this. Next thing is what happens when it's not at that particular angle. Let's draw in a normal over here, and let's draw in an angle of incidence in a different color. So I'm going to draw in one over here like that, in the purple color. Now you can see that the angle of incidence is not 0. I'll draw in the angle of incidence. There's the angle of incidence there. Now, what happens is very critical, and you need to understand this very clearly. You've got to recognize that when waves enter a different medium, there is a change not only in the speed, but if it's at an angle, some of the waves can start to turn and they can start to bend. The reason we say this is happening is because we think about waves traveling in a long train. Although we've used an arrow to represent a wave, what we can actually think about the waves doing is moving along in fronts or sets. Now, you might have seen this on the beach, where waves move from far out at sea into the shore, they then tumble and they roll, and then the next one comes in. We call that idea where all the points are doing the same thing. They're moving in phase next to each other. We call that a wave front. Now, you can imagine what happens when a wave front hits the surface. What's going to happen is that some of the wave front is going to be in the material and some of it's going to be out in the air. What's going to happen is that this part of the wave front that's in the material is going to slow down. This part is still traveling fast, but they're next to each other. So what does that mean? If this one is slow and this one is fast, so this is still fast, but this is slow, then if you've got an arm that's going slow on the inside, it bends. It has to catch up. The fast bit moves quickly and then it catches up. The result of that is that it's going to bend. In which way will it bend? Well, it will bend towards the normal on the other side. And that's exactly what we want to show. That over here, when we're going from fast to slow, then it bends towards the normal. In other words, it doesn't carry on in the same direction as it was going. And I'm going to just draw a little white line over that line. We might have expected the light to travel in that direction. I haven't drawn it very well. I want to draw it straight. There it goes. We might expect it to travel straight. No, it doesn't. It bends towards the normal. Now, when I say bend toward the normal, what do I mean? Let me show you. It's going to close this angle. It's going to get closer to that dotted line, which I have drawn as the normal. So, can you see that? It has struck at that point, and instead of being this big angle all the way through to there, it's not. It's only half of that. It is smaller than it was. This green arrow that I've drawn in, or this green line here, represents the angle theta of refraction. And in this case, angle theta was smaller than the angle of incidence. Why? Because the wave was slowing down. It was moving from where the refractive index in air to the refractive index in glass. And what do we know about this? That the refractive index in air was less than the refractive index in glass. So, hope you've got all those relationships clear, and you can see how we've drawn the picture. But look, there's something else. You need to understand that this light doesn't just get trapped inside the Perspex block. It strikes the parallel surface. So we're going to need another normal. And I've drawn one in there. Let's just get my drawing very good and accurate. I'm going to just move this line so it is exactly on top of the normal. Now, again, what you should notice and what you should recognize is that this line doesn't carry on in the straight direction as it was going before. Okay? It was going in that direction, and what you need to recognize is that it doesn't carry on going as it was going inside the material. It doesn't carry on going in that direction. Make it very clear for yourself. We don't normally draw in these little white lines. I'm just wanting you to see them. And I found it's helpful to show the direction. The light doesn't go in that direction. Remember, it's now going from moving slowly, to speeding up. So which way is it going to happen? The light, again, is going to bend. In this case, it doesn't bend towards the normal, it bends away from the normal. The amazing thing here is because the lines are parallel, the sides of the Perspex prism are parallel to each other, it will continue parallel to where it originally went. So I'm going to get that parallel line, and the way I'm going to do it is I'm just going to move that line into position over there and then put the purple line on top of it so that you can see the direction. So what happens is it's going to go in that direction like that. Excellent. How would we describe that? We would say that it has moved away from the normal. That this second angle of refraction, that would be called angle of refraction 1. This would be angle of incidence 1. This angle over here, when it comes to the second surface, angle of incident 2, and this one would be angle of incident of refraction 2. And what you'd need to recognize here is that for the second one, the angle of refraction number 2 is greater than the angle of incident number 2. It's moved away from the normal. Why? Because it is now speeding up. Guys, if you can get this picture and you learn this picture of exactly what's happening, we can worry about the size or the magnitude of the angles a little later. We'll come to that directly after this. We're going to do the calculations of this in our next session. So don't miss that. Guys, you need to understand exactly what's happening when it's moving from air into an optically denser medium like glass. Then it's going to slow down. It's going to move towards the normal. When it's moving from glass into air, then it's going to speed up. It's going to move away from the normal. If you can learn that, then the mathematics will fall into place, and you'll be able to do the calculations as well. Okay, so let's just mention one other thing, and I want to emphasize that. Hopefully you can see that here, this was a rectangular prism. this line, these sides, were parallel to each other. And I hope you can notice that the incident ray, this one coming in, and this one leaving the block, which is sometimes called the emergent ray, they are parallel to each other. If we trace back where we might think this one has come from, we might think it's come from somewhere back here, but if you notice that, it's parallel to the original one, more or less parallel to the original one. And you can do this practically and show that they just deviated a little bit, but they're parallel to where the one was coming in. They're in the same line, but they've just moved a certain distance away. So if your eye is over here, you will think that the light is coming from somewhere back here. That's where you'll think the light is coming from. You won't think that the source of light is over there, but you'll see it in the same direction, parallel to where it actually is. Very good. I hope you're with me still. Now, the next part of the theory is, say, if we do a practical investigation like this, then we'll be able to verify, measure the angles, measure exactly what's happening, and come up with the law of refraction. The law of refraction is also known as Snell's law. So there are two parts to it, very much the same as the law of reflection. The first part says when light travels from a material with a refractive index N1 into a material with a refractive index N2, so like air into glass, the refracted ray, the incident ray, and the normal to the interface between the materials all lie in the same plane. Okay, it's quite a mouthful, but the meaning is clear. They're on a piece of paper. They don't bend in strange directions. They follow through in a logical way. You can take a ruler and you can measure them. You can show them on a piece of paper. The second one is the more interesting one mathematically. It says the angle of refraction, theta r, is related to the angle of incidence by the following equation. N1 times sine theta I is equal to N2, the refractive index of material 2, times sine theta of the refracted angle, the angle of refraction. So material 1, this is on the incident side, and this is on the inside, on the after refraction. This is when refraction has taken place. Refraction has taken place. And so it's easy to separate it. This is before, this is the picture before, and this is the picture after. And we're saying that those two factors, the refractive index, are related to the angle of incidence and the angle of refraction. Make sure you've got that very clear, and make sure that you understand it in terms of our diagram. Let's just go back and have a look at the diagram, see what we're relating. We're saying this particular angle is related to that value on this side. This angle is related, this angle here is related to that value there. It's always related to the angle of incidence and the angle of refraction. Please just make note that you've got the correct angles. I want to just highlight them again so that you've got them very clearly. So it's the angle, of incidence over here, and the angle and the refractive index, and the angle of refraction at this surface, which is this little angle over here, and that refractive index. Please take note of that and make sure that you understand those. Of course, we could have done it at the other interface, but I'm not going to do that right now. Let's move on. And here we have a question for you to consider and look at. Not only a question, but it will help you apply what we've already done. It also gives us some more information. So what it tells us, it says to us that we are required to draw a diagram to show the path of light passing through a triangular prism. So there's our triangular prism. We're not told about the refractive index, but for the moment, let's presume that it's glass or perspex or one of those where it is going to cause the light to change its speed. So what happens? Let's get it very clear. We recognize we have a normal, and we recognize that we have an angle of incidence. So there's my theta I. We're not required to do the calculation. So I'm just going to draw in some lines to assume where things were going and where they should be. So I like to draw that line in to say, well, the light was heading roughly in that direction. I want to get it as accurate as I can, move it up, and I'll say, guys, I've got it on the green line. We'd expect the light, if there was no refraction, to emerge somewhere over there. But unfortunately, that's not what's going to happen. What's going to happen is there's going to be refraction. And the first thing is we're going to say, let's assume, as I mentioned earlier, that the refractive index of this particular substance, don't know what it is, but let's say that it's greater than 1, 2. Let's say something greater than 1, 2. So what we recognize here is this is the refractive index of air, and we're going to say we know that is 1, 0, and we're going to assume that the refractive index is greater than 1, 2. Just bigger than air. Let's make sure that it is bigger. So when it's bigger, it's more optically dense. We know it's going to bend towards the normal. The angle that it bends towards the normal we can calculate using Snell's law, but for the moment I'm going to just make it like that. I'm going to put it into position on that point, and I'm going to say, let's get it as accurately as we can onto that line. Now, if you're using a protractor and a ruler, you'll be able to get it much more accurately than I can on this board, because the board is sometimes a little slippery. Okay, there we go. We've got the light has bent. How is it bent? Describe it. It is bent towards the normal. The angle of refraction at this first surface is smaller. The angle of refraction at the first surface is less than the angle of incidence at the first surface. It's bent towards the normal. Now, let's pick up a normal and let's put the normal line in for our other object over here. So we want a line that's perpendicular. Well, that wasn't the one that I wanted. Let's pick up the correct line, that one, and we want the dotted line at 90 degrees, something like that. If it's moving from a more dense, remember this is more dense, this is more dense, more optically dense. How can I say that? Because I know it's greater than 1, 2, to less optically dense, to less dense, less optically dense. Then how is it going to bend? It's going to bend away from the normal. In other words, it's not going to carry on going in a straight line. It's not going to follow that path. But what it's going to do, it's going to bend downwards. It's going to bend down like that. Now, very important. I just want to move this line and delete it because it's not really necessary. But what I want you to see is what's happened here is that the light has changed direction. This prism has changed the direction of light. The light was going in this original direction, the first one. It was going here. This is the original path. And here's the new path. What's interesting is that on a triangular prism or any shape, when the sides are not parallel, we can get light to change its direction. we call the angle between the original path and the emergent ray, we call that the angle of deviation. And so you need to take note of that. That angle is known as the angle of deviation. Excellent. So make sure that you can draw these diagrams. They are really important, and we'll get to the calculation parts where you can fill in the numbers a little later. Right, moving on to our next idea, and this is also related to triangular prisms, the idea of total internal reflection. And here is the critical thing, and it's important to say critical, is that sometimes when light is inside a closed surface, when it's inside an object, and I'm just going to use this one as an example and say, if light is inside this prism, and let's say that the beam of light is moving from a very high optically dense material to air. So it's moving from a dense side to air on the outside. It could be something that's just less optically dense. At this point, the light is in and it's trying to get out. Now, under certain conditions, what we will find is that the light doesn't emerge. What does happen, though, is that it undergoes internal reflection. And in this case, the laws of reflection will apply. And that's why we started with the laws of reflection, just to make sure that you remember that the angle of incidence in this case will be equal to the angle of reflection. So here, the angle of incidence, and that's the angle in R. No, it says R, but it's reflection in this case. So angle of incidence is equal to the angle of reflection because it's total internal reflection. This can happen inside a prism, it can happen inside a diamond, it can happen inside a glass fiber. It's very, very important idea and very important and useful principle. But when does it happen? Well, there's a critical angle at which light will not escape from the material, but it will have an angle of refraction equal to 90 degrees. And if it has an angle of refraction equal to 90 degrees, that angle is called the critical angle. So the critical angle is the angle when the angle theta of refraction is equal to 90 degrees. So when an emergent ray is coming out of a surface, and what we would find is it bends away from the normal, so it will follow, that's the angle of refraction, we would say 90 degrees along the surface. It's not happening for this particular one. The angle of incidence here is greater. So when the angle of incidence is greater than the critical angle, then you'll get total internal reflection. Excellent. So be very clear about this. It only happens when we're moving from an optically more dense to less dense, high refractive index to low refractive index. And the second condition is that the angle of incidence must be bigger than the critical angle. So if the angle of incidence is bigger than the critical angle, then it will work, then we will get it. So in this diagram, if this was the green arrow, I've drawn them the wrong way around, let's just get the green arrow in. The green arrow is showing you the critical angle. Then when the purple arrow comes along, it's bigger than the critical angle, and so it undergoes total internal reflection. Right, let's see where we can apply this. We're going to apply it to our question. Question number 2. draw a diagram to show the path of light passing through a triangular prism. The critical angle for this prism is 42 degrees. Now, this particular triangular prism, I just want to add in some markings to make it a little bit clearer, has a 90, and to make it absolutely no mistake about it, let's say that this angle is 45 degrees and that angle is 45 degrees as well. So it's an isosceles triangle, and it's an isosceles right angle triangle, and we are quite clear that everything is given to us. So bearing that in mind, what's going to happen? How are we going to work out the path of light? Now, let's go through it and let's see. Where the light is currently shown on the green arrow, you should recognize that that is making a 90-degree angle. So let's be very clear there. We're going to say that that angle there is 90 degrees. Tells us the angle of incidence is 0. So the angle of incidence is 0. Remember, when the angle of incidence is 0 and light is passing into a transparent object, it will continue. It's not going to deviate. It will still undergo refraction. The speed of light will still change, but it's going to continue straight. So I'm going to just pick up that line and I'm going to extend it. Hopefully it will extend. There we go. And it's extended nicely for me. Now it's come to this position. I hope you can see that the angle now of incidence should be very clear to you, that if I've got a 45 degree and a 90 here, this angle between the ray and, let me just draw it in pencil, in a different color, this angle should be 45. Okay? So if that angle is 45, then if I draw in the normal, I hope you can see that the angle of incidence to the normal now, the angle of incidence. Please notice that that yellow line was not the angle of incidence. It was the angle between the surface and the incoming ray. It's not the angle of incidence. The angle of incidence here must be 45 as well, because the normal makes up 90. 45 plus 45 gives you 90. So I'm going to write this in green. So that's the angle of incidence. And what do we see? The angle of incidence here, which is equal to 45, is greater than the critical angle, which was equal to 42 degrees. So what's going to happen? What do you think? Remember, if the angle of incidence is greater than the critical angle, total internal reflection will take place. If we're moving from a more optically dense medium to a less optically dense medium. So in what they should have told us, well, they kind of did with the critical angle idea, but they should have also perhaps given us the idea that this has a refractive index greater than 1,0. And this is in air and so on. So I'm just going to move this because I know that I'm going to need that particular area to complete the diagram. I'm going to move it and put it into a different space. I'm going to say this angle of this prism is going to be greater than 1,0. So it's moving from in this case, less dense to more dense. It's moving from fast to slow. And it would have gone fast here, but it can't, because the angle of incidence is greater than the critical angle. And so what happens? It gets bent back. Refraction still takes place in a kind of a way, but it causes it to be refracted back into the medium. And so what do we know about the laws of reflection? Laws of reflection tell us very clearly that what's got to happen is that the angle of incidence which we already know was 45 degrees, has got to be equal to the angle of reflection. So we know that the angle of reflection on the inside has to be 45 degrees, which means that when we draw in our reflected ray here at this point, it's going to form a 90-degree angle on the inside there. If it forms a 90-degree angle, this angle is 45 degrees. It means it's going to be at 90 degrees to the other surface. And look what's happened. It's going to go straight out because the angle of incidence here is 0, and 0 is less than the critical angle. So it doesn't bend back inside, it goes straight through. Okay, what's the end result? In this particular prism, in an isosceles right-angled triangle with this particular critical angle, please notice something. The angle of deviation is 90 degrees. The angle of deviation, light was traveling in over here, and it's come out over here, so it has bent through an angle of 90 degrees. Angle of deviation is 90 degrees. Now guys, this is very useful. It's used in all sorts of optical instruments, and there are many others. You can bend light through 180 degrees. That's one of the principles of binoculars. Shortens the path length so that you can see at a distance using lenses. Very important idea of total internal reflection. Modern application of total internal reflection is in fiber optics. The glass cables that carry your telephone signal are bending light internally, carrying the signal inside. We also use fiber optics, or medical practitioners, doctors, surgeons use fiber optics to do internal procedures where they can look at what's happening on the inside of our body. It's a breakthrough in medical science that we can use this amazing phenomena to our advantage. So light is really wonderful. Now, here's the last principle or the last property of light that I want to go through. And the property we're going to look at is the property called diffraction. So first of all, let's ask the question, what is diffraction? We know about reflection, we know about refraction, but what about diffraction? Now, don't get them mixed up. I know they have fraction at the end, they have some common words, but they are very different. Diffraction is a very interesting phenomenon, and it happens for all waves. I'm going to explain it very briefly, and hopefully you'll be able to have a look at it. So, we're not going to talk about light for the moment. We're going to first of all concentrate on just ordinary waves. Let's imagine that we have a set of water waves that are moving in a particular direction. And I want to just put those water waves in, and I'm going to push them next to each other like that. I'm looking at the water waves from the top, and as I mentioned to you earlier, what we're doing is we're getting the top view here. We are wanting to see that these are evenly spaced between them, and we call these waves, they're known as wave fronts. You can imagine all of these points here being a crest. In the middle, between the crest, we would get a trough, and then here's the next crest. So the white lines simply represent particles that are in phase with each other. They're all crests. Okay, so this is a crest, the little dot represents a crest, and they're moving in the same direction. They're moving from left to right, they're moving in that direction. Now, the question that we've got to ask ourselves when we come to this terminology for diffraction is what happens, can we explain what will happen if these wave fronts meet a barrier. So I'm going to pull in my barrier, and I'm going to say, there's my barrier. What do we expect to happen? Well, this is what I would expect. It's not necessarily what does happen, but I would expect that behind the barrier, in that region, the light or the waves would bounce up against the barrier, and they would be reflected. So we recognize the little waves would travel in that direction, and they'd simply be reflected off. And we wouldn't be wrong. That's exactly what happens. So what happens to this section of the waves? If that was a wavefront at that point, let me just draw it in white. If that was a wavefront, what would we expect? Well, we'd expect it just to travel straight through. And so the waves would split. Some of them would go through, and some of them would be reflected and stay behind. And so we might expect and predict that we would get a pattern of waves looking something like that on the other side of the barrier. But you know what? Something very interesting happens. It doesn't work like that. What happens is that there is a bending of light, of waves, behind the barrier. So they move into this region of space. The waves start to move into the region behind the barrier. So this doesn't stay totally still. Now, the question is, does this happen with light? Now, yes, it does. And there have been some amazing photographs, and you can perhaps even go and Google these or look them up on a search engine, where you look for images of diffraction of light. And there are countless ones. One of the most interesting ones that I found is that people did some experiments in a photo lab, and they took a pin and they put it in front of a very narrow beam of light. So there was a very narrow beam of light, and they had a screen over here, and what they expected was different to what they got, because what you might expect is a shadow to form on the screen, and that's explained because light travels in straight lines, and so we would expect this area here to be all light. Okay, so shining light, shaded in yellow, just so that you can get the idea that, and in the middle you would get a black shadow. Okay, they'd got their cameras all set up, and that's exactly what they're expecting. You know what they found? That right in the center of the pin, there was a little, and I've exaggerated it now, a little tiny dot of light. What did that tell us? That light had bent around the pin from both sides, top and bottom, all the way, and created a tiny little dot of light. A tiny little dot of light is evidence that diffraction had taken place. But scientists earlier in the centuries didn't have the advantage of this practical experiment. They didn't have the photographic equipment. And so a long time ago, 1800s, people did experiments with diffraction, with light. They created little gaps, and that was the one thing that I needed to just emphasize here. That's one example of light, of diffraction. There is a second type of diffraction where instead of having a bending light around a barrier like that, like I've just shown you there, is that there is another option. The other option is to create a little gap, two barriers, if you like, two little barriers. And scientists like somebody called Young and another guy called Fresnel did a whole lot of experiments on these. And there are our wavefronts. That one wasn't very straight, but anyway, we'll just leave it like that for the moment. And what they found was that light, or waves, when they pass through a gap like this, another man that was very responsible for experimenting this was a man called Huygens, Dutch man. He found that if you had a wide gap, let me draw a wide gap first of all. So if you have a wide gap, you would get diffraction like this. just a straight bit and then a slight bending on the corner, and a straight bit and a slight bending on the corner, and so on. But if you narrowed the gap, if you made the gap much smaller, smaller than the wavelength, and you made that gap very small, I'm going to do it down at the bottom. I'm going to take my barrier, take it away, and move it down to the bottom. So now here, second experiment, and I'm making my gap smaller. My wavelength is still there. My pattern I'll put in place. So what happens here? Well, when the gap is very small, you get more diffraction. This is what they found. There is more diffraction. And what happens is we get this happening. We get circular waves entering the pond. Now, you can test this even in the bath. Go and look and see. If you make some barriers and look at them, look at it in a tub of water, you'll see a ripple effect when you make the slit smaller. So when the slit is much smaller than the very small, you get more diffraction. Now, what does that tell us about light? Well, we know the wavelength of light is very, very small. But if we can get the gap small enough, then we find a very interesting pattern that emerged. And I want to just sketch this for you and explain it a little bit. Here are our wave fronts. We have to use, or it's better to use, light of the same color. So this is red light, and it's usually produced by a laser. It's easier because then it's all of the same frequency and it's all in phase and it's all happy. And I've drawn the slit very big there. But what we would notice is that we get a strange pattern projected onto a screen. We get a very bright central band, and then in between it we get some dark bands. Okay, and then this is a bright central band, bright red band, bright big band. Then next to it we get a smaller, this is a dimmer, it's dim, red band, and notice it's smaller, and so the pattern spreads out. This is evidence that light undergoes diffraction. Huygens explained it, and Fresnel explained it as well. We don't need to go into too much of the explanation. All we need to say is that this is evidence that light is behaving like a wave. Isn't that amazing? There's one last diagram that I just want to show you related to that, is that you can sometimes be given in a diffraction pattern, is to say, when diffraction takes place, they'll show you intensity of the light. They'll show you something like this, and then like that, and then like that, and like that, and like that. And this is really about the brightness of the pattern. This is about the intensity or brightness. So what they're saying is here, this is the broad, the central band. This, where it almost touches the bottom, that's the dark region. And then this is the second band, which is not as bright, it's dimmer. And then this is the third one, which is smaller and also dimmer. The reason this takes place is because light is undergoing constructive and destructive interference. It's giving us evidence that light is behaving like a wave. Now, later you will learn that light also has a particle nature. So let's not forget that. We eventually come up with the idea that light is a fascinating topic that we can explain with different models, with a wave model and with a particle model. But enough from me for today. It's been great being with you. We've covered the main points of today's lesson. Join me next time when we do some calculations relating to these different aspects. We'll see you again.